Now, ice is, well, ice is the name of a bounty hunter in the TV show Arrested Development, but we're not going to be talking about that ice today. Instead, we're going to be talking about ice, the form of water in a solid state. Water has many different crystalline forms. The hexagonal ice is the most common. Hexagonal ice forms an organized lattice and thus has a very low entropy. Hexagonal ice contains a maximal hydrogen bond slash water molecules, forcing the forcing the water molecules into equidistant arrangements. So this basically has ice has low density compared to liquid water, which when you think about, if you get a glass of water, what happens whenever you put, or a glass of ice water, what happens when you put the ice in there? It floats up. Okay, it's all because of this solid, crystalline structure. Now, when you think about a ice cube, essentially what you have is something like this. You have multiple sheets of these different kind of layers of water molecules that are hydrogen bonding with one another, and then those are hydrogen bonding with adjacent water molecules that are hydrogen bonding with other adjacent hydrogen bonding molecules. Other hydrogen bond based water interactions. So it's kind of a complicated network that connects all of these different molecules. But one of the things that I want you to take away from this is there's a good chunk of space away from between all of these different water molecules. Now, especially if you go back and you think about the distance or the length of those covalent bonds compared to those hydrogen bonds. I know that this is not demonstrated for scale, but it's worth noting that you have these water molecules fairly well separated from one another. Water is a great solvent for charged and polar substances. So amino acids, peptides, small alcohols, carbohydrates, all of these things that we will be talking about in this biochemistry class. Water is a really bad solvent, or maybe I'm going too hard on it. It's a poor solvent for nonpolar substances. So nonpolar gases, aromatic moieties, aliphatic chains. So this aromatic moieties is going to come in play when we talk about some amino acids, so the R groups of some amino acids. So some, I'm going to say AAR groups. Okay, so water is not necessarily the best solvent for those. So what does that mean for those? Well, they're probably going to pack tightly with one another. Okay, so some examples of polar versus non-polar substances. So our polar substances with these alcohols would be glucose. Glycine is an amino acid, an N termini and a C termini. Those are going to be great for hydrogen bonding. Aspartate, lactate, glycerol, these are all great for hydrogen bonding with water. Compared to a wax. So wax is an example of a lipid with these long chains down here of a bunch of hydrocarbons. Next up, phenylalanine is an amino acid that has an aromatic moiety. Aromatic. And then phosphatidylcholine is another example of a molecule that has these long non-polar groups, but then it's got a bunch of it that's very polar. So that's going to be great for hydrogen bonding with water. Okay, the physics of our non-covalent interactions. So non-covalent interactions do not involve sharing of electron pairs based on their physical origin. One can distinguish between them. Ionic interactions, dipole interactions, van der Waals interactions, hydrophobic effect. Okay, so if I were to say that some of these were more important than the others, I would say that the most important is probably going to be, or the most important two are going to be your ionic interactions and your hydrophobic effect. Because most of what we'll talk about with respect to interactions is we're going to be focusing on interactions between different amino acid R groups. And I know we haven't introduced the amino acid R groups, but we will, I promise you. Ionic interactions, well, we have some amino acids that are going to be negatively charged. Those R groups are going to be negatively charged, so they are going to be an anion that's loving to interact with a cation. Hydrophobic effect. Well, we just saw phenylalanine as an example of an amino acid that has a hydrophobic R group. there are a number of other amino acids that also have those same hydrophobic groups, and they're going to love to interact with one another. So will dipole interactions and van der Waals interactions, those are just maybe not as significant in terms of protein structure in interactions between different amino acid R groups. So I'd like you to be sure that you remember ionic interactions, a cation and an anion are going to interact with one another. Hydrophobic effect, you have the ordering of water molecules around nonpolar substances. Nonpolar substances are going to want to interact with other nonpolar substances. Some examples of non-covalent interactions. Well, I just said ionic interactions. You've got attraction between a positive group and a negative group. You've got repulsion between two positively charged groups. Then hydrophobic interactions. Well, two groups that are, these are two different amino acid R groups, that they're going to be very attracted to one another because of the fact that both of them kind of, I hate to be rude like this, but they don't care for water. They'd prefer to be around other hydrophobic residues in these hydrocarbon dense regions. Van der Waals interactions, any two atoms in very close proximity, but that's, again, I would focus my time on these guys right here, because I think that's going to be the most valuable in terms of appreciating the types of interactions that we'll see. Dissolving salts involves breaking ionic interactions, so a high dielectric constant reduces attraction between oppositely charged ions in a salt crystal. So almost no attraction exists whenever you have a large distance. And I don't know, well, I know that we don't really look at this in Gen Chem 1. I'm not sure what class that you would necessarily look at it, but this right here, this is looking at, you have oppositely charged ions, a positive and a negative, and what our denominator here is talking about the distance ultimately that we get these two ions away from one another. So strong electrostatic interactions between solvated ions and water molecules lower the total energy of the system. So water is able to use a negatively charged end of itself to basically attract a cation. And so these water molecules are able to disrupt ionic interactions between something like NaCl or other ionic compounds. So water, here's what we've got. We've got this NaCl crystal and these individual water molecules that, well, they've got a dipole, and so they're going to position the partial positive end toward that chloride ion. Likewise, they'll position partial negative end towards the positively charged sodium ion. So that's how water molecules are able to disrupt ionic compounds. Okay, van der Waals interactions have two components: your attractive and repulsive forces. So London dispersion forces are also known as your attractive forces, and steric repulsion, which depends on the size of the atom, that is your repulsive forces between two atoms. So attraction dominates at longer distances, and repulsion dominates at very short distances. Van der Waals interactions, like I said previously, they're relevant and they're significant, but they're not I guess kind of a big ticket item when it comes to amino acid interactions and protein structure.